Hello, advanced algebra students. I am so happy to be teaching you your first lesson. I obviously would prefer if I could see you in person, but I'm happy that we are all keeping safe by doing distance learning. We are going to do streamlined versions of notes and distance learning. In other words, I'm not going to include as many examples as I normally would, just because I do understand it takes longer when you're trying to take notes by video than you might if we were working in a classroom environment. So I wanted to let you know the notes are going to be streamlined. I also wanted to give you a couple tips. So one of them is it can be most helpful to watch this video on a device where you can zoom in or zoom out. The reason is that I'm using something called a gimbal to record these videos. So see, I can walk to the right and walk to the left, and the video camera is following me so that you can always see what I'm writing on the board. But because I need to do that, I'm having it track my eyes, and if I were to put the video right in front of me when I was writing on the board and turned back to the board, the video would stop recording me moving because it would not see my eyes anymore. So I've got to have the gimbal going at enough of an angle that I don't lose contact with my eyes in the screen. So I do understand it's at a little bit of an angle here, but you can zoom in using either a phone or an iPad or something like that so that you can see exactly what's on the board. The other thing I want to say to you, which I know is obvious probably, but please do feel free to pause the video as much as you need to. I do want to keep the length down, and so I am going to go at a fairly good pace, and if it is too fast for you, please just hit the pause button, get what you need written down, and then push play again. All right, I can't wait to see you in Zoom, but we are going to start our first lesson. You're going to write at the top of the piece of paper 1.1 operations on real numbers. So first what we've got to do is define what real numbers are. So what I'd like you to do is in the middle of your paper somewhere, write the numbers 0, 1, 2, and 3. Put a circle around that. We are going to call that set of numbers whole numbers, W-H-O-L-E. And the way I remember this, I know it sounds a little bit corny, but I just remember that 0 looks like a whole. And so I know that the list of numbers starting with 0 and going to the right on the number line, not including decimals or fractions, is the set of whole numbers. The next set above that is a set of integers. So go ahead and write -3, -2, -1, 0, 1, 2, and 3, ... And then draw a circle around that. That is your set of integers. Now the way that this diagram works, it means that the integers include 0, positives, and negatives, as well as all whole numbers, which would of course be 0 and positives. So we're building up and getting bigger and bigger sets that always include the subsets below them. All right, above integers, we're going to write the word rational. The key to understanding rational is seeing the word hidden in rational. If you circle the first 5 letters of rational, it forms the word ratio. So a rational is simply any number that can be written as a ratio or a fraction. So for example, it could be 1/3 or 1/4. Now, just because the number is rational, however, does not mean that it has to be in fraction form, just that it can be written in fraction form. So if it's written as a decimal, we have some rules about it that must be true. So for example, let's take the 1/3 that I already put up there. If you type 1 divided by 3 into your calculator, it's going to say 0.33333. So it is 0.3 repeating. And if you type 1 divided by 4 into your calculator, it's going to say 0.25, which doesn't repeat, but it stops. So the way that we know a number in decimal form is rational is that it either repeats or it stops. So for example, 0.33 repeating or 0.25 and done. So that would be all of your rational numbers. Now in a separate circle from the ones you've just drawn, I would like you to do another circle and call that irrational. By the way, hopefully this is all review for you. All of chapter 1 pretty much should be review for you, but I just kind of wanted to give you a reminder. Okay, so irrational numbers, you can probably guess, are different than rational. Anyone want to take a guess how you would know, looking at a number in decimal form, that it's irrational? What do you think would need to be true about it? So if rational numbers have to stop or repeat when they're in decimal form, with an irrational number, the decimal does not stop or repeat. Can anyone guess what one of the most famous irrational numbers all of you already know is? What do you think is one of the most famous irrational numbers? The one that goes on and on forever without repeating. Many of you may have guessed pi. Pi, as you know, is 3.14159 blah, 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 but it goes on forever and ever and ever. It never stops. So we're going to call that a rational number. Another very common example might be the square root of 2. If you type the square root of 2 into your calculator, it will go on indefinitely without repeating or stopping. And so we know that that is an irrational number. Not all square roots are, because for example, square root of 9 is just 3. That would be a rational number. In fact, it would be a whole number. Okay, now if you draw a big circle all around both of these circles, that would include all the real numbers. So we've just finished doing a mini lesson on what the real numbers are. Now, we do talk about several properties of real numbers in this section as well. And I am going to go kind of quickly over them because again, this is all review, but this will be on your homework and I wanted to make sure that you understood it. The commutative property basically tells us that the order doesn't matter. So for example, I'm going to put 2 examples of each. 3 plus 4 is the same thing as 4 plus 3. With all of these properties, we're going to talk about them in the context of addition and multiplication. These properties are not typically going to be true with subtraction or division. So the commutative property of addition would tell me that 3 plus 4 is the same as 4 plus 3. Can you think of an example with multiplication? Let's do 3 times 4 is the same as 4 times 3. So it's the same idea that order doesn't matter, but you're using multiplication. Okay, let's do the associative property. The associative property means who associates with who doesn't matter. And again, if we were teaching in class, I have silly little examples and stories to go with all these, but in the interest of time, let's just put an example here. Let's put 1 plus 2 in parentheses and then say plus 3 equals 1 plus, and then in parentheses 2 plus 3. Notice that both sides say 1 plus 2 plus 3, but how I grouped the numbers has changed. So with the associative property, you change your groupings, but you do not change the order. So if we want to do an example of the associative property of multiplication, we could do, again, maybe 1 times 2 in parentheses and then 3 outside of it. And then on the right side, 1 times the quantity and then in parentheses 2 times 3. Okay, let's do another property, the identity property. Basically, this one is telling you that the number does not change. So an example of the identity property of addition might be that 7 plus 0 equals 7. Can you think of an example of the identity property of multiplication? We might do 7 times 1 equals 7. So for multiplication, it would be times 1. Okay, the inverse property. The inverse property tells me that I basically undo whatever I do. So for example, 5 plus negative 5 equals 0 would be an example of the inverse property of addition because I'm getting rid of the 5 that I started with. With multiplication, it might be, for instance, 4 times. What do you think I would take 4 times in the context of multiplication? It'd be like 4 times a quarter equals 1. And then the last property, which everybody should know, is the distributive property. An example of that, which falls under both categories, might be, for instance, 2 times the quantity x plus 3. When you distribute, it becomes 2x plus 6. So that should be familiar to all of you. Now, I'm just going to do a few examples with the time that we have left. Again, I do want to have the notes be streamlined. And then what's going to happen is that we are going to flip this classroom. So we're going to do the lesson the night before by video, and then during class, we are going to go over the homework at length. All right, so let's do, for example, if we want to compare and order real numbers. So have this be example 1. Let's do the square root of 4 over 9, 1/4, and 0.6. If you were asked to order those numbers from least to greatest, what I recommend doing is changing everything into a decimal form and then figuring out the order from there. So if you turn 1/4 into a decimal, it becomes 0.25. And then the square root of 4 over 9 becomes 0.67. So then we can see that 1/4 is the smallest number on the list, so it should be first. And 0.6 would be next, and 0.67 would be last. So it's easy to tell what order to put real numbers in if you turn them all into decimals and then just go from least to greatest. Okay, now let's look at example number 2. If we have an algebra expression or a combination of numbers, how do we tell whether they're rational or irrational when we're adding, subtracting, multiplying, or dividing? So let's do example number 2 here. Let's do 3/5 plus radical 2. Do you think that would be considered a rational or irrational expression, and why? 3/5 plus radical 2. That would be considered irrational because when you take the square root of 2, you would get a decimal that keeps going on forever. And even though you're adding a rational number to that, the fact that one of them is irrational is going to make the entire thing irrational. Now here's kind of a trick question. Can the sum of 2 irrational numbers ever be rational? So is there any number, irrational number, that I could add to this one that would give me a solution that would be rational? So let's do, for example, 3. Can you have the sum of 2 irrational numbers be rational? Question mark. Can the sum of 2 irrational numbers be rational? The answer is yes. It doesn't typically happen, but let's use the number we had above, 3 plus radical 2. How about if 3/5 plus radical 2? How about if I add to that 2/5 minus radical 2? What would happen here is I would have a positive radical 2 and a negative radical 2. The square root of 2's would cancel out, and I could combine the 2 rational numbers that I have left. So 3/5 plus 2/5 would be 5/5 or 1. It doesn't always have to equal 1. I just thought I'd make it come out kind of pretty. Okay, the last thing I have on the notes here is understanding sets and subsets. And by the way, I'm reading from a much more extensive notes that we are not going to do because, like I said, we're streamlining. We're doing fewer examples and just kind of highlights, and then we'll go over more detail in the homework. But I did want to talk about sets. So a set is a collection of objects such as numbers. An element of a set is an object that is in that set. So for example, let's make this example number 4. If I want to make a set and call it set A, so example 4, set A, I could say that set A consists of the numbers 1 through 10. So you kind of show those little brackets like that, and that would be a set. Now set B would be a subset of A if each element in B is also in A. So let's do a subset B of the even numbers in set A. What would that be? If I want to do a subset of A and call it B and have it be all the even numbers, that would just be 2, 4, 6, 8, and 10. And then let's have set C be the numbers that are multiples of 5 in set A. So if set C is the subset of set A that is multiples of 5, what would it include? It would include 5 and 10. And then the last question I'd like to ask is, which number is the only number that is an element of both sets B and C? The answer would be 10. 10 is the only number that is in all 3 sets. All right, so that was the gist of the notes for 1.1. Thank you so much for listening to these and taking good notes, and I can't wait to see you in class. Have a good rest of your day.